Okay. Assalamu alaikum, everyone. Welcome to our lectures on this lecture on selected topics on radiation physics. This is lecture number 11, and it's just a continuation of the past lecture. Are the slides visible to all of you?
Yes, doctor.
Okay. So last lecture, we talked about cavity theories, and we said there are actually three cavity theories: small and large, and then there is an intermediate cavity theory. And the small cavity theories, we said, okay, there are two basic theories: the Bragg-Ray cavity theory and the Spencer-Attucks cavity theory. And for the theory to be valid, okay, there are two requirements. The first one, or postulates of the theory. The first one for small theory is that the ionization produced in the cavity is actually from charges produced outside of the cavity. And the second theory is, the second postulate is that the presence of the cavity does not perturb the fluence. And then Spencer-Attucks took this one further step, and he took into account these delta electrons that are produced in the tracks of charged particles. And the assumption is that these delta electrons, they will actually escape from the cavity and will not deposit any dose in the cavity. And they are thought of or included as part of the fluence that is actually entering the cavity. And from there, we started to apply, look into, for example, when we have a chamber with a wall, what would be the dose inside the chamber, following the small cavity theory as well as the large cavity theory. Remember, when we have a chamber, air surrounded with wall and with medium, our interest is to know the dose when the chamber is not present, neither the air nor the wall. But the ionization in the air cavity will be produced by charges coming from the medium as well as charges coming from the wall. And the assumption is that the air, no charges will be actually created inside there. So if you had a photon beam, essentially the photons do not actually, they're blind to the air. They don't interact with the air. But the ionization in air is produced by the charges that are produced elsewhere. And we took these basic assumptions, and we found then what would be the dose in air, taking into consideration the charges produced in the medium as well as the charges produced from the wall. And we rewrote actually that equation. So this is basically the dose equation. So if we know the dose in the cavity, then the dose in the medium will be given by this relationship, where alpha is actually the fraction of the dose that is deposited by electrons produced in the wall. And we rewrote this long equation in the Spencer-Attucks form, where the dose in medium is given by the dose in the air cavity, or dose in the gas, multiplied by the stopping mean stopping restricted stopping powers of medium to gas, multiplied by a perturbation factor, a small perturbation factor. And this perturbation factor is then going to be given by this relationship. So essentially, this perturbation factor is called P1. Okay? If the wall is very, very thin, then alpha is going to approach 0, and then all of this factor will become 1. So we retain back the pure Spencer-Attucks relationship between the dose in the gas and dose in the medium. So in our assumption, Spencer-Attucks, is that, okay, the presence of the chamber does not actually perturb the fluence. So the fluence essentially at the point in medium compared to the fluence in the chamber, they're essentially the same. That's the assumption in but in reality, this is not true. So again, we need to apply another correction factor to account for the presence for the chamber there. So think about it. Imagine if you have photons. Let's go back to this slide. So imagine we're looking at, for example, the photons or electrons coming to this point in medium there, those. So if we correlate this point to a point here in the cavity, we will see that the fluence is going to be perturbed because the attenuation, think of just the attenuation of the photons and how electrons are interacting. They're going to go through different medium compared to when the chamber is not there. So definitely there is going to be a perturbation. And this is called a P replacement. So for example, so this correction factor is used to account for this replacement of the phantom by the ionization chamber when we're doing the measurement. Okay? And this perturbation factor is really not big. So this is from an older protocol. This is TG21, where they are showing, they're plotting actually the P replacement correction factor as a function of the diameter of the chamber. So the larger the diameter of the chamber, okay, the more there is air, and we would expect then the effect of the presence of air is going to increase, going to be larger. This is why this perturbation factor, as the diameter increases, we find that the perturbation factor actually it deviates more than from 1. Okay? Ideally, you want this to be 1, but the effect, and this effect also will depend on the beam energy. And here, for example, the worst would be for cobalt. That's about 2% difference, or effect is about 2% for cobalt. Higher energies, this effect is less important. So then we can modify the dose equation, the P word, as well as this P replacement correction factor. So similar to the P word, the wall correction factor will depend on the design of the chamber, as well as on the beam energy or the beam quality. The P replacement, again, is another factor that will depend on the ionization chamber, as well as on the beam energy. So both of these two factors, they depend on the beam energy as well as on the chamber. However, the restricted stopping power ratios, this factor, it only depends on the beam energy. So if I use two different chambers, this factor is going to be the same when I use both of them to do a measurement in the same beam. However, the P-wall, P replacement, each chamber will have a different P-wall and P replacement depending on their design. There is also another correction factor, perturbation factor. This is specifically when we have cylindrical ionization chambers. So in the cylindrical ionization chamber, we have this external wall, usually it's made out of graphite, and then we have a central electrode, so a needle-like inside of the chamber. So this correction factor is needed when the materials of the central electrode and the wall, they're not the same. So for example, if the central electrode is made out of aluminum, whereas the wall is made out of graphite, then this we will need to account for this And this is in this p-centered electrode. Again, it's a very small correction factor. But in order to get the dose as accurately as possible, one needs to account for such things. But if the center electrode and the wall material they made out of graphite, then this perturbation factor is equal to 1. It's not. Okay. And obviously for parallel plate ionization chambers, this correction factor is also not given. It's equal to 1. So finally, we get this dose equation. Again, this is the Spencer Attucks. And then we have a P-wall perturbation factor, a P replacement, and a P central electrode. P central electrode, again, will depend on the chamber as well as on the energy, the beam energy. So all of these three factors here, P-wall, P replacement, and P central electrode, they are chamber dependent and they are energy dependent. However, the restricted collision, this is the restricted collision stopping powers of mass to gas. This parameter depends on the medium or sorry, it depends on, obviously it depends on the medium, but also it depends on the energy, but does not depend on the chamber. So now we want to move on how to determine. So this is the equation that we're going to be using, okay? So now we want to see how we can determine the dose in the gas cavity in ionization chambers. Okay? So the dosing in the air-filled ionization chambers, when the chamber is irradiated, then what is produced inside the air cavity are positive and negative ions. The reason why we don't have positive and negative electrons, remember when we have ionization, essentially we're freeing an electron from air molecules. So it's to have positive ions, that's trivial. But to have negative ions, well, in air, we have oxygen molecules. And oxygen, they have a high electronegativity. This means that an oxygen molecule would actually grab a free electron and becomes an ion. So this is why in air, usually we have a positive and negative ions rather than positive and negative electrons. If we had a chamber filled with nitrogen gas, gas has a low electronegativity. It does not it will not attract or attach a free electron to the molecule. So in nitrogen gas, for example, essentially the charges produced in the cavity and the gas cavity would be positive ions and electrons. Okay, so that's the difference between nitrogen and air. So in air, in order to produce an ion pair, it's estimated that the average, we will need on average an energy of 33.97 electron volts per an ion pair. So if we want to know what is the energy deposit in the cavity, all what we have to do is just, okay, count how many number of ion pairs that were produced, and then multiplied by the energy required to produce an ion pair. So basically, this is the energy absorbed inside the cavity. We can rewrite this by multiplying this. We multiply the number by electron charge, so we get the charge Q of the ions that are produced, and then we divide by E here, and then we get this constant value. This is W air over E, which is the mean energy required to produce 1 coulomb of charges. Okay? This factor is essentially energy independent. It does not matter except for very low energy, I think very low energies. But this is a plot of the WR. It's essentially constant here. It's about 33.97, unless the electrons will have a very, very low energy, then the amount to produce an ion pair is, on average, the energy is going to, this amount is going to be higher. So think about it. If an electron has a low energy, it cannot really ionize air easily. Okay, it does not have sufficient energy to ionize the air molecules. So many of the interactions will not actually produce ions. And that's why it tends that this factor actually shoots up at very low energies. So this dosimetric sign Q is actually the charge of one side. So either we take the positive or the negative. So we count all of the positive charges or the negative charges, and that will be actually the dosimetric signal. Here, this is Q is the dosimetric signal. So if we know Q, this is a constant for air. Other particles, for example, they might have a different value. So here is actually for electrons. So electrons, that means photons also, because photons produce electrons. But if we had an alpha particle, if we had protons, for example, this W air over E might be different. It's not going to be 33.97. It's going to be a different value. And if you're interested, you can look at the ICRU 31, where they discuss actually this factor in depth. So for air, we have W air over E, and the SI unit for this is 33.97 joules per coulomb. In other words, in order to produce 1 coulomb of ions in air, the radiation needs to deposit an energy of 33.97 joules. So then the dose deposit in the air cavity is therefore going to be Q multiplied by this factor, which gives me the absorbed energy in the cavity. We then need to divide by the mass of air. Absorbed energy divided by the mass, this is the dose. So this is how one can obtain the dose in air. This is a constant. All what we need to do is to know what's the mass of air in the cavity, as well as the ionization produced by the radiation beam, and this will allow us to determine the dose in air. So one can say, okay, the mass in air, since the chamber has a volume, then we can actually rewrite the mass of air as the density of air multiplied by the volume of the chamber. For vented chambers, so if you have a chamber that is open to the environment, temperature and pressure, affects then the density of air inside the chamber, then this density will change, will vary. However, if we had a sealed chamber that is not open to the environment, then the density of air will remain the same. It does not change in sealed chambers. It changes when for open chambers or vented chambers. So this is one issue, one thing also one has to be careful with. Another issue is that this volume is actually not the physical volume of the chamber. It is the volume from which the charges, when we do our measurements, we're going to collect the charges, the ionization produced in the chamber. And depending on the chamber design, the volume from which the charges are actually collected might not equal to the physical volume of the air cavity in the chamber. Therefore, in general, this volume is very difficult to determine in an ionizing chamber. Also, you can think of it, manufacturers, when they produce a chamber, they cannot guarantee, even for the same chamber model, that the air cavity volume is actually going to be exactly the same for all chambers. So there is going to be small variations there. But the main reason is because of we're interested more on the collection, the volume from which the charges, when we do the measurements, the charges are actually collected from. So one way to determine this volume is an indirect method, is actually by send your chamber to an accredited dosimetric laboratory, ATC, and what they do there, they will actually give you a calibration, give you a factor for the chamber. This factor is called an N-gas. N-gas is basically given by this here. This is constant. V depends on the chamber volume. And then we have the density of air. Furthermore, if the chamber is open to air, open to air, then the density of air will change depending on the temperature and the pressure. So they should also indicate the temperature and pressure at which N-gas was obtained. Or they will give you actually N-gas at a NTP. This is the temperature. It's a reference temperature and pressure. Then when you actually use the chamber in the clinic to do another measurement, and if your chamber is open, then you will need to somehow correct this N-gas to an N-gas valid at the environmental conditions when the measurements were done. But if you had a sealed chamber, you don't need to do this correction. They will give you the N-gas. N-gas could be used at any temperature and pressure because the mass of air inside the chamber is not going to change. So the N-gas calibration coefficient, therefore, it's energy independent. Why? Because of the formula. We have the W air over E. This is energy independent. And the density of air has nothing to do with the beam energy, and the volume of the chamber has nothing to do with the beam energy. So this factor is energy independent. It doesn't matter at which energy they obtain this N-gas, or you can take it and use it regardless of your beam quality or energy. The chamber, this factor obviously is going to be chamber dependent because the collection volume, okay, it varies, it depends on the chamber design. And this factor, as I mentioned, it's going to vary with air temperature and pressure for vented chambers. But if we had sealed chambers, this factor is constant, does not depend then on the temperature and pressure. So if we had a vented chamber, how we then do a correction? How do we calculate an N-gas that is valid for the environment at which the measurements are being done? So this is basically, we need to apply a correction factor. It's called PTP, temperature and pressure correction factor. And you can think of this PTP in two different ways. Either you can think of it as a correction to the N-gas. So the reference, for example, in the certificate, when you obtained their N-gas, they will say this N-gas is at temperature 22 degrees Celsius and 1 atmospheric pressure. Or if this is actually in the States, North America, 22 is the reference temperature. But if you're in Europe, the chambers, they will provide N-gas at a reference temperature of 20 degrees and still 1 atmospheric pressure. So always look at these things. Where was the chamber calibrated? If it's in North America, the reference temperature is usually 22. If it's in Europe, it's 20, because that makes a difference on this when you calculate the temperature and pressure correction factor. So one way to think of this is this PTP is actually a correction to the N gas at the reference environmental conditions to the measurement environment conditions. Or you can think of it as basically we're trying to predict what would be the signal that we would have measured if the temperature and pressure at measurement, they were actually exactly the same as the temperature and pressure, the reference temperature and pressure provided by the standard slab. So either you can think of it as a correction for the N gas, or it's a correction to the signal. So how would this obtain? Well, at typical room temperatures, air could be treated or thought of as an ideal gas. And this is the equation for an ideal gas, PV equals to nRT, and from which we get that the density of air is going to be proportional to the pressure and inversely proportional to the temperature. So if the pressure increases, then the density of air increases. If the temperature increases, the density of air decreases. So this density is somewhat related to N multiplied by R divided by V. So NR over V, that is you can think of it, it's something related to the pressure of the gas. So the density, if we want to calculate a correction to the density at room temperature, our measurement conditions compared to the reference conditions, we can just take the density of air at our temperature and pressure. So this is our measurement conditions divided by the density of air at the reference conditions. This is basically given by this relationship. Note that in this formula, the temperature are in kelvins. They're not in centigrades. Okay? So the temperature and pressure correction factor, then it's given by this relationship. It's P reference divided by P. So this the pressure, the reference pressure, usually it's 1 atmospheric pressure. And then the pressure, this is the pressure when the measurements were done, multiplied by T plus 273. This is T is going to be in Celsius, and plus 273 just to convert it into kelvins, and divided by the reference temperature plus 273. You can put 273.2, that's okay, or 0.15, it's okay. But the point is that this reference condition, take care of it. Reference temperature. If the chamber was calibrated in North America, this reference temperature is 22 degrees. And if the chamber was calibrated in a lab in Europe, this is 20. And you can see 20 or 22, it changes slightly this heat temperature and pressure correction factor. So notice there are, if you look at this is the correction for the density. So the reciprocal of that will be actually the P temperature and pressure. So now the dose in air, we said it's the charge multiplied by the N gas. But if N gas, if the chamber is open to air, and N gas will be established at a standard or a reference temperature and reference pressure. And then when we do the measurements, in general, the temperature at of the measurement conditions, they will not be the same as those at reference conditions. Therefore, one needs to apply a temperature and pressure correction factor in order to obtain the dose in air. And again, I want to emphasize, if the chamber is air sealed, then this temperature and pressure factor is not required, okay? Because the mass of the air in the cavity is not going to change.
Sorry, Doctor, I have a question.
Yes.
So in the same equation, when we have B and air, and that we have N and gas, both of them, they're gonna have the same constant, which
What's
it's
that?
gonna
Say again. Say again.
D air
D air. Okay.
and N gas in the other side of the equation.
Okay.
And both of them, they're gonna have the same constant, which is
What
WA or divided by E. Yeah,
what do you mean same constant?
which is W divided by E, W air. We go back to the few little equations you show.
Let's go back. Cannot go back.
Okay.
Yes. Okay.
One more.
Okay. This is N gas.
So, yes, we have N gas here. We have the constant W divided by E.
So
W air.
this part. So this here. This is N gas.
Okay. And then D air
Okay.
V. Okay. Okay. The constant will change. This is in gas.
No, there are no. I don't see what's this constant you're
Okay.
talking about.
Okay. Go. This is the air. Yeah. You see,
This
density multiplied by volume, and WA W air
W air over
divided
E.
by.
This is constant, right?
This is constant for dA. Then we go for N gas equation.
Okay, this is N gas.
The same constant.
But I told you this, all of this here, this is N gas.
The only difference here is the Q and the number one.
Q is okay, what charge you're going to measure. So now you put the chamber in under ionization or in a radiation beam. Ions will be produced in the air cavity, right? So
Yeah,
the
so now,
number of the charge produced in the air in the cavity, this is Q.
okay, now, for the N gas equation, we don't have a charge. We have one.
N gas is not a charge. It's not something related to what the charge produced. It's a conversion factor. So if we have a charge, we convert that to, it's a conversion per 1 coulomb. So N gas has a unit, usually the SI unit for it is going to be joules per sorry, it's going to be joules per kilogram
Without a charge.
per coulomb. So it's going to be joules per kilo. That's the SI unit. Joules per kilogram per coulomb. Okay.
There's no charge. We have a charge units. There's no charge. You know what I mean? You know what I'm trying to ask?
No, I don't know.
So we have joule per coulomb.
That's the W air over E, right? This W air over E, the unit for it is joules per coulomb. Okay?
Okay.
So the SI unit. The volume, the SI unit for it is meter cubed.
Okay.
And the density, the SI unit for it is going to be kilograms per meter cubed. Okay?
Okay.
So N gas, the unit for N gas, the SI unit for it is going to be joules per kilogram per coulomb. So when
what's
we
the difference? This is my question exactly. What is the difference in the units here and in the units there?
What is here and what is there?
Yes, in the units, because it sounds to me, I look at it, that Earth should have charge, but they don't. They have one.
What should have charge? Still,
N gas.
N gas is per charge, per coulomb.
There's no charge.
It has a unit. This W air over E is joules per coulomb, right?
Yes, yes. But what is W air per air? But this is W air per air was the amount of energy required uh,
So we have
to create
W
an
air.
ion.
This is W air only. Okay.
Okay.
W air. This is 33.97 electron volts per ion.
Per ion.
Per ampere. Okay.
Okay.
W air
Divided by E.
over E. This is 33.97 joules per coulomb. Okay. So instead
Okay.
of we're counting ions, we're saying, okay, each ion has a charge E. So we're
this is
multiplying.
the required energy to create an ion
This is W air, right?
in the air.
So
Yes.
to create 1 coulomb of charge in air, this is the factor.
Need this.
W air
Yes.
over E. Okay?
Beautiful.
So
To create one
coulomb, not one charge, coulomb.
So to create what's the difference between 1 coulomb and 1 charge? Because coulomb is a charge.
Coulomb is charge, but it's a unit, right? But there is an ion pair. I would say electron has a charge +1, but +1 what? What's the unit for that? So the unit for charge is coulomb. So the charge of an electron is 1.6 10 to the power minus 19 coulombs. But here I'm saying it's electron volt per ion.
Yeah, clear.
Okay.
Okay. Okay, I can. So here, this one here has no charge on it, but
This the
express
unit
it.
for the N gas, the unit for it, the SI unit. Let's go back. So the SI unit, let's clear this. The SI unit of N gas is going to be joules
Per column 2.
per coulomb. So it's going to be joules per kilogram per coulomb. That's the SI unit for N gas.
N gas has no charge.
What do you mean has no charge? I still don't, it's a calibration, it's a conversion factor. N gas, the SI unit for it is joules per kilogram coulomb. Or often what we do, the more common way is N gas. The units for it is going to be usually it's in centigrades per coulomb. Or sometimes it's grays per coulomb. So this should be small letter. This is centigrades per coulomb or grays per coulomb. Okay. So essentially, if we have a charge Q, we multiply it by N gas. Okay, this is
Convert.
going to give me the dose in air. This, the unit for the charge, this is coulomb, and the unit for N gas, this is grays per coulomb. So when you multiply, you see that this goes with this and you get the gray. Okay?
Okay, okay.
Okay. So how does a chamber actually work? Okay. So essentially a chamber is a capacitor. So we have air and we actually polarize. We put a voltage on one of its electrodes and then we get a capacitor. So when the capacitor is charged, no current is going to flow between here, and then the reading of the current is essentially zero. Okay. This is the configuration, how an ionization chamber is connected in a standard configuration. The chamber will have 3 electrodes. We will have a polarizing electrode, we will have a collecting electrode, and we will have guard electrodes, or sometimes they're called guard rings when in the parallel plate ionizing chambers. So what we do, we have a power supply, and this power supply then will polarize the chamber. So here, for example, we can have a positive voltage, and here is negative voltage, or zero, grounded. And also, yeah, so this is going to be, based on this configuration, this is going to be grounded. So this potential there will be zero, whereas the power supply will polarize, put a potential on this polarizing electrode. So what happens when the chamber is polarized and we get ionization produced inside the chamber, then ionization will be produced in all of the cavity, or everything that has air, ions will be produced. However, since the electrode guard and the collecting electrode are separated, they're not in contact, then we take the signal only from the collecting electrode. Essentially, these are the ions that are defined by this volume here. So ions will be produced there, but they do not contribute to the signal. We're not interested in measuring them. So the issue for a chamber is really to determine this volume, this collection volume. That is why if we could actually determine this volume, then we can apply, we don't need to send the chamber for calibration. We can just apply the equation to determine the dose in the gas. And all what we need to do is then determine this volume, if we could. But this is very difficult. And that's why we have to then send the chamber in order to determine this volume in an indirect way, where they give us a coefficient, this N-gas coefficient. So now when the chamber, when we put a plus V voltage, what's going to happen? We're going to polarize this. We have a positive charge on this electrode, and then the radiation will produce ions in the chamber. When the ions are produced, the positive ions are going to go down to the negative electrode, or the negative voltage, and the negative ions are going to be attracted. They're going to go to the positive, to the polarizing electrode. So all of these positive charges that are going to land in this electrode, that constitutes our dosimetric signal, because that's the number of ions, or it's related to the number of ions produced in the air cavity. And essentially, the positive charges and the negative charges produced in the air are essentially the same. Okay. If we reverse the polarity of the chamber, again, using the standard configuration, so this is negatively polarized. So here we have a negative voltage here. And what's going to happen is that the negative ions, now they're going to land on this electrode. And the charge, or the signal that we're going to record or register by the chamber, is going to be the negative charges. The positive charges instead. So essentially, if we repeat, we have the same irradiation, and in one setup, we put this at positive polarity, positive voltage. The charge that are going to be collected here is going to be a positive charge. So the signal will be plus something coulomb or nanocoulomb. And then if we reverse the polarity, the charge that is going to land at this electrode will be the negative charges. So the signal will have a negative sign, minus something coulomb. Okay? So you can see the difference between the two. But sometimes, for some ionization chambers, they are actually configured in a reverse configuration or non-standard configuration. So now they move this power supply and they put it behind the electrometer here. Actually, there is something wrong in this design. This actually, we should move. So this here, okay, maybe I cannot do it quickly. It should be here. That's the correct design of the chamber. Because we need to maintain both the the guard electrodes and the collecting electrodes, we need to maintain them at the same voltage. So the voltage across these electrons has to be the same. So in the reverse configuration, they are the same, but then again, we have our electrometer collects the charge only that is collected by the collecting electron. But the point I want to make sure to emphasize here is that now when the power supply is at plus voltage plus, then the bottom these electrodes will have a plus voltage. And what's going to happen is that the negative charges, they're actually going to be attracted. So the signal we're going to collect will be the signal of the negative charges. If we reverse just quickly. Sometimes I just copy and paste and then take care of the text, but not the drawing. I apologize for this. So when we put a negative voltage, then these electrodes will be at a negative potential, and the charge that we're going to attract or going to be collected will be positive charge. So actually, when you use a chamber, you can determine if this chamber is actually connected in a standard configuration or in a reverse configuration. All what you need to do is put the potential, let's say 300 volts, and look at the sign of the signal that is collected. If it is positive, then it's in the standard configuration. If it is negative, then it's in the reverse configuration. Okay? And so this is in a reverse. So even although the positive, we have a positive voltage, but we are actually, or the signal that we're going to collect is going to be the negative ions. So there are some signal corrections that are required for the chamber. Remember, the dosimetric signal, all what we want to determine is the number of ions produced by the radiation beam inside the air cavity, inside the chamber. So that's our dosimetric signal. However, what we measure here, the signal that is collected by or registered by the electrometer might not necessarily equal to the signal or the charge that is produced in the cavity. And there are two effects that are usually two effects that will result in this. And this is the first one is ionic recombination, and the second one is polarity. There are some polarity effects. So in ionic recombination, what happens? Ideally, we want to collect all of the charges of one sign that is produced in the chamber. But it happens as the chamber is polarized and the charges are moving towards the opposite electrodes. They might actually meet with one another, and then they exchange the charges that they have and become neutral. So because of ionic recombination, we are actually going to lose some of the charges produced in the cavity because these charges have combined with one another. And this will essentially result in that the measured signal is going to be less than the dosimetric signal or the charges produced in the chamber cavity. There are two categories or two types of ionic recombination. One is called initial recombination, and one is called general recombination. So initial recombination happens or describes when actually ions from the same track recombine. So if we think of we have the charge particle, so we have our electron, for example, or a proton or whatever. It's a charged particle. As it's going through air, then it's going to ionize the medium air. Okay? And we get positive and negative charges produced within this track of our charged particle that is crossing the chain. So when charges produced from the same track recombine with one another, this is called initial recombination. This is important if we have a densely ionizing charged particle. For example, if you have an alpha particle or maybe protons, because the density of these charges on the track is going to be high. So the likelihood of them meeting with one another and recombine is going to be high. Okay. Or if we have a dense gas, we have a gas that is very, very dense, then again, the ionization track in the gas is going to be very dense. So this is initial recombination. General recombination, okay, this should be general recombination. Is actually, we're still, charges are combining with one another, but the charges were produced from different tracks. Okay, so we have one track here. So it can happen that an ion, a positive ion produced within this track is going to recombine with a negative ion produced from a different track, from another track. Okay, this is called general recombination. This effect, the probability of it happening will depend actually on the number of tracks. The more tracks we have, the more likely, or that general recombination is going to happen, going to occur. This is why this recombination effect, it depends on the dose rate. And dose rate, I don't want to think of a linear of 100 mUs per minute to 600 mUs per minute. No. A correct wording for this would be the ionization density. How much ionization is produced in a pulse? So if we have a LINAC where it's a pulse beam, if the ionization ionization density is very high, then or actually this general recombination will depend on the ionization density or the number of ionization tracks within the cavity. Since this is in general, this general recombination is dose rate dependent, but luckily for us, for a typical linear accelerator, it doesn't vary really much because usually the ionization density is really not that high in the cavity. However, newer LINACs, newer treated machines, for example, like flash radiotherapy, or if we look at those electron mobile LINACs that are used in surgery, interoperative electron LINACs in IORT machines, the dose per pulse is actually very high. So general recombination in general will be affected a lot by the dose rates of these machines. It's a big problem, especially when we, for example, want to commission and measure percentage depth doses, which I'm going to talk about next session. There, if we're measuring percentage depth dose for an electron beam, for example, so the density or the ionization density will vary if we are at Dmax or let's say at R50. It's a big difference between the two. And since general recombination depends on the number of tracks or the ionization density, then the ionization or the correction factors for general recombination will not be the same. This is why the recommendation when one is commissioning such machines is to use appropriate chambers. For example, they recommend in electron beams to use a 1 millimeter ATIX, advanced ATIX chamber, where the separation is 1 millimeter, because the smaller the chamber is, then the faster we're going to collect the charges and giving them less chances of actually meeting and recombining with one another. So it will affect this general recombination. The bottom line, one has to be careful of the ionization density produced by the beam. In general, for a typical accelerator, although it occurs, it happens, but the probability of it happening really does not vary much with, let's say, dose rate, because essentially the dose per pulses roughly does not vary a lot. But the exceptional part is when we have these new machines, either an IORT machine or a flash radiotherapy machine, where the ionization density is very, very high, then in general, one really needs to take very great consideration when calculating, corrections for the combination. So ionization chamber, if one, for example, plots a signal versus voltage, I mean, if we want to reduce the probability of recombination, one would need to collect the charges as fast as possible, not giving them any chance to meet with one another and recombine. But there is always a limit. So this is the signal, plot of the signal versus voltage in ionization chambers. So this region here usually is called the recombination region, and this is called the saturation, or sometimes this is where the region where typically when we do dosimetry, measure doses with chamber, we operate the chamber at voltages in this region here. So if one is tempted to increase the voltage in order to reduce ionic recombination and collect charges fast, it could happen that the voltages applied could actually give or accelerate the ions to an energy where these ions could then ionize the gas. Okay? And this is why we see as the voltage increases beyond a certain limit, we start to see that the signal is going to increase. So the signal in this region is not from the ionization produced in the cavity by the radiation beam, but also the ionization produced in the cavity due to collection, due to accelerating the ions when we're collecting them. There are definitely some applications of ionization chambers when they're operated in this region and in the Geiger region, but this is the region in general where we want to operate our ionization chambers in order to determine the dose. Okay, so this effect we call it charge multiplication. Okay, so a single charge produced in the cavity will actually further produce other charges or due to being highly accelerated because of the high voltage used in the collection process. So if we had a plot, so this is in general, this is if we have a voltage and we have a charge, and imagine we have the steady beam. The beam is the same. The ionization produced in the chamber is the same. And all what we're doing is looking at the signal that we're collecting as a function of voltage. We get an increase, and then we have this plateau, and then this is the region where we want to operate our chamber. In this region, there is a lot of recombination happening. We're not collecting the charges fast. But still, this does not give us exactly the charge that is produced. Still, there is somehow some recombination happening. It turns out that if you plot 1 over Q and you plot 1 over V squared, So this is, we have a continuous beam, for example, over 60. Okay. The plot will look something like this. So at low voltages, if we're here, this is 1 over v squared, and here we're talking about here. So one way to determine actually the signal is we can look at this linear region and we can start to fit this to a straight line.
Excuse me, sir, if you can get the microphone just nearer. Thank you.
So in this region, we can fit the data with a straight line, with a line. And the intercept of this line, this is actually, so instead of 1 over q, this is one of the signal. It's this is the measured signal. Okay. So if we extrapolate, we are going to get this q. And again, the same here, thing here, this is the signal. Okay. Because q, this is the charge produced by the radiation beam. The challenge is, okay, we need to collect it. That's the whole idea. So what we measure is a signal, M. And M, the signal that we're going to collect will depend on the polarization of the chamber. So in this region, this is where we have a straight line. We can then extrapolate and get our Q. And this is why, for example, we use this 2 voltage technique. So we can, instead of, a line, we don't need to measure all the points in the line. We can determine this equation of a line using 2 voltages, one at a higher voltage and one at a lower voltage, and we can determine the equation of the line and extrapolate and get the intercept, which is the reciprocal of the charge that is produced. For pulse beam, the same thing happens, but it is 1 over v. Okay? It's not 1 over q, 1 over v squared. And there is actually some fundamental physics why it's 1 over v squared and 1 over v. So in a LENAT is general, it's the pulse beam. Instead, we have this region where we can extrapolate and get here 1 over q. Okay. The general recombination, just to give you a brief idea, the general recombination actually in continuous beam, it varies or it's 1 over v squared. In pulse beam, it is 1 over v. So that's why we get these scares. There is some fundamental physics actually behind this. So this is a plot. This is a continuous beams. So for example, in a cobalt beam, or even if we have a orthovoltage machine, orthovoltage machines are considered continuous beams. And this is a plot of 1 over q versus 1 over v squared. Again, you see this, the data points, and you get almost like a straight line. So the idea is just extrapolate this line and get the intercept. The intercept is 1 over the dosimetric signal. Or if instead we want to use the 2 voltage technique, we can do that. But often the practice is that we use a signal, one signal, and calculate a correction factor for it. So that's often what's in protocols. So again, what we need to do is to measure a signal at a high voltage and another signal at a low voltage. And then we are going to use the signal MH as our measured signal and apply to this signal at the high voltage a correction factor. And this correction factor is given by this relationship. This relationship one can derive just by looking at getting the same concept. Define the line by 2 points, and then get the Q sat. So the product of the signal at high multiplied by this p ion, this essentially is going to give us the dosimetric signal Q. For pulse beam, it's the same concept, but all what we need to look at is 1 over Q or 1 over M versus 1 over V. Again, there is a straight line, and then it decreases. So this is the multiplication region, okay? Because we are plotting 1 over Q versus 1 over V. So higher voltage, we're going down. As we increase the voltage, we're going like this, okay? And again, using this concept of two voltage techniques, one can derive this simple equation for p-ion. So again, multiplying the signal obtained at high voltage multiplied by this correction factor p-ion will give us the dosimetric signal. So it's up to you. Either you can use this line and extrapolate and get the signal here. That is your dosimetric signal. Or what you can do is get a correction factor that you need to apply to the high the signal measured at the high voltage. There is another, looking at the IATRS protocol 398 protocol. They also recommend, so basically now they're saying this p-ion is really is given by a quadratic equation with parameters A0, A1, and A2, and these parameters A0, A1, and A2 are coefficients. This will depend on the ratio of the applied voltages. So if we're using, let's say, a 400 volts at high voltage and 200 volts at low voltage, then the ratio is going to be 2. Then for that ratio, we need to select these parameters and apply it in this equation with the signals MH signal obtained at high voltage and one at low voltages. I've never used this equation. I always like to use the two voltage technique. I cannot comment which one is accurate, but there is essentially no difference between the two, almost no difference. So whether you use this equation or the one with the two voltage technique, that is still valid. No problem with that. What about heavy ions? Okay. What do we do with these heavy ions? In heavy ions, initial recombination cannot be ignored. Not like when we're doing air cavity chambers and electrons, for example, or photon beams. In heavy ions, of course, it produces a densely ionizing track, and initial recombination essentially cannot be ignored. So the recommendation is, again, you plot 1 over M versus 1 over V, similar to the pulse beam, and what you do is then you extrapolate to V equals to minus to infinity to get the reciprocal of the charge. So this is based on the protocol TRS 398. You don't use, they don't have a formula like for pulse or continuous. Their recommendation is just plot this versus 1 over M versus 1 over V and extrapolate to V equals to infinity.
What M stays for?
M is the signal.
Oh, the whole signal.
The signal that you're measuring, the measurement signal.
Oh, yeah.
Okay.
Okay.
And here they put it as current, which is fine, because this is what you're measuring from the electrometer. Okay.
Okay.
So what they basically, you fit it to this line, and then this is the intercept, right? 1 over the saturation. This is what you're looking for. The I think they call it I0 here. This is I collected, and this is I0. So essentially, it's a straight line, fitting of a straight line. Okay. So how about polarity effects? Polarity effects. What is a polarity effect? So basically, when we collect the signal, when we measure the signal, sometimes the charge that we measure when the chamber is positively polarized, so at this polarization is different when when we reverse the polarity of the chamber. Okay, this, I think there is something wrong here. These errors should be the opposite. The positive signals should come down here. So in general, when measured signal at opposite chamber polarizations, they're not equal to one another. This means M plus and M minus, they're not equal to one another. Then the chamber is said to exhibit a polarity effect. Okay.
I think there is
But-
no error in the slide before, Doctor. Because you can see here, this positive you pointed at is repelling from the negative there.
I said
Trying
this,
to-
Muhammad, if you listened, I said this. I
Did
said,
you?
yes, I said that these errors are not correct. The errors should be reversed.
No, I'm saying it is correct.
No, it is not.
Because you see, for example, the one
this is
you're
positive. This is positive, right? Positive charge.
Yeah, but repel
Positive-
from the one under it.
Positive
Elec-
charge. A positive charge should move towards the negative electrode.
There is a
Okay.
negative electron here. Make it repel to go up. You see? You know what?
This here is correct. We have here a positive charge, so the negative charges produced in the chamber, they're going to be attracted. They're going to move towards this electron.
Yes.
These negative charges. Here, the figure is not right. The negative should move towards the positive.
Yes. Oh,
Okay.
yes. Oh,
Okay.
yes. Yes.
Okay.
Yes. Yes. I see it now. I see it. Sorry.
Okay.
Sumimasen by Japanese. Sorry.
Okay. So polarity effects, there are actually voltage-dependent polarity effects. Voltage-dependent means that this polarity effect will depend on the applied voltage. It's not constant, or it's not the same. Okay. So for example, this could be caused by distortion of electric field by potential difference between the guard and the collecting electrode. Remember, we said here, so we have a guard. So there might be a distortion. There might be, the lines of electric field might not be exactly straight like this, but, there might be a distortion. Might not be exactly like that. Okay. And this amount of distortion will depend on the voltage applied. So that's why it's a voltage dependent effect. Another thing is the space charge distortion of electric field lines defining the gas sensitive volume. So when the chamber is not ionized, we have electric field that is set by the polarization of the chamber. But now when we apply the ionization radiation beam and we get ionization in the chamber, so now the chamber has charges inside, and these charges can distort actually the shape of the electric field inside the chamber. Okay. And again, that effect, how much distortion is happening, that depends on the magnitude of the electric field. Usually, if the electric field is high, they should have a lesser effect on the distortion. Difference in mobility of positive and negative ions. So ideally, when we have positive and negative ions, we want to have, if the speed, imagine if the speed of the negative ions when we in the electric field is faster or higher than the speed of the positive ions. So we are going to collect them, when we collect the negative ions, inside the chamber is no longer neutral, but we have an excess of positive charges inside. So that could also affect, the electric field inside the chamber. So, and these three effects are, in general, they depend on the applied voltage in the chamber. But we have one that is independent. It's a voltage independent polarity effect, and this is caused by radiation-induced currents. Usually, they're called Compton currents. Essentially, what's happening in this Compton current is that when the radiation, the chamber is in the radiation beam, this is our collecting electrode. So we can have, for example, ionization in the electrode itself. So we're going to have charges produced in the gas cavity, but in the electrode, we can have ionization there too. Imagine if we have a photon coming, and it can interact directly with the electrode, leaving a positive charge, because electrons will be ejected, and then we have a positive charge here. So when we have this, what is the signal that we're going to measure? So the signal that we're going to measure, if we have this, imagine this is a positive polarity or polarization, then the negative charges are going to be attracted there, and the positive charges of the ions are going to be attracted towards the collecting electron. But the signal that we're going to measure will be the positive charge plus the signal that is induced inside the wall. Okay, and this signal is not dosimetric. We're interested in the charges produced in the air, not the ionization produced in the electrode. Now, if we reverse the polarity, what's going to happen? Well, the negative charges are going to land here, and this is going to be attracted there. So the signal that we're going to measure is going to equal to the negative charges plus this Q. These two Qs, they are the same because they depend on how much ionization produced in the electrode by the radiation beam. Has no, does not depend on the voltage applied. Radiation is produced by radiation interaction in the electrode. So in one case, we're going to find M plus is going to be larger than M minus. Why? Because this has a negative sign. So imagine if Q plus is 1 coulomb and Q minus, because these should be the same, Q minus is minus 1 coulomb and Q is 0.1 coulomb, then what we're going to measure is going to be 1.1 coulombs when we have a positive chamber, positive polarity, and when we have a negative polarity, we're going to measure minus 0.9 coulombs. So the absolute values of these charges that we're measuring, they're not equal to one another, and the chamber will exhibit polarity effect. So how to correct for this? Well, very simple. The correction is very simple. We can, because we're interested in, let's say, the charge Q plus. That's the one sign. That's the dosimetric signal. We could apply the same concept if we are interested in what is Q minus, because they are the same, okay, in terms of magnitude, but opposite signs. So what we can do, Q plus will be just simply, we can subtract the two signals that we're measuring, divide by 2. This will give me actually Q plus. And again, following, the way that we like to rewrite our equations is we convert this to a correction factor to the positive charge. Okay, so this is the correction factor. It's often called the polarity correction factor. So when we multiply the P polarity correction factor by the signal that we have measured at M plus, this should give me the dosimetric signal of Q plus. So just to sum up, to wrap up everything, this is the equation. This is the N-gas formalism. So the equation, the dose in the air cavity in terms of N-gas is going to equal to N-gas multiplied by some corrections to the signal. The P-ion, because this is the signal we're measuring, P-ion. We have the P polarity, polarity correction effect, and then P temperature and pressure. So in this case, we're thinking of this P temperature pressure as a correction to the charge, or we could think of it as a correction to N gas, as discussed earlier. But we're not interested in the dose in air. We're still interested in dose in medium. So let's grab this N gas from the equation, and then N gas will then, then we want to convert the dose in air into dose of medium. That's I think the second equation on the second or third slide. So we have all of this part. This represents dose in air multiplied by the Spencer-Attucks ratio of restricted solvent powers. And then we have the P wall, P replacement, and P central electrode if the central electrode and the wall of different materials in ionization chambers. Looking at this equation, we find that N gas is a factor that depends on the chamber only. Does not depend on the radiation beam. The ratio of restricted solvent powers, this depends on the radiation beam. It does not depend on the chamber. And then the remaining these correction factors, P wall, P replacement, and P central electrode. All of these three factors, they depend on the chamber as well as on the radiation. So this is a big advantage of determining the dose with N gas. N gas is energy independent. But the problem we face is that now we have to determine all of these factors for the chamber and for the radiation beam quality. Now, there is a new formalism, and this is often what you will be applying in clinics. This is the used by the AAPM TG51 or with the by the IAEA TRS-39A. So essentially, what they have done is that they've taken all of these factors. N gas was multiplied by all of these factors, and they said, okay, this now we're going to define a new chamber calibration coefficient, and that calibration coefficient is called the dose to water calibration coefficient. It's by NDW. So now N gas and everything after it, that is absorbed in this new dose to water calibration factor or calibration coefficient. The rest, something related to the charge, polarity, and temperature and pressure for open chamber, all of this remain the same. Now, N gas, NDW, this is the formula for it. But what is differs from N gas, that this factor depends on the beam quality, on the radiation beam, as well as it depends on the chamber design. So if you receive a certificate with an NDW, this certificate must state the energy, this beam quality for this NDW. It must specify that. Usually, they take a reference beam, they state it's cobalt. So they will give you an NDW for cobalt. Okay, but the nice thing is it's very simple. If we have a cobalt beam and we want to know the dose, all what we need to do is just multiply the signal, correct it for temperature and pressure, ion and polarity, and multiply it by this factor. Only one single factor. That is given by the dosimetric lab. Whereas if the dosimetric lab gave us an N gas, then we need to figure out all of these factors. They will not give us, in general, they will not give us these factors. But you could find these factors, for example, in these protocols, TG21, or TG25. And I think the TRS-277, I think if I'm not mistaken, that's an older protocol, is also based on N gas. They had a different notation. It's ND air, actually, I think they call it, if I'm not mistaken. So although the N gas is a a nice factor, could be applied to any radiation beam, with any radiation beam. The difficulty that we usually face is to determine all of these other factors on that chamber and beam. NDW, they solved this problem. They gave us one factor, and that's it. As long as the beam we're calibrating the chamber in, or we're doing the measurement, matches the beam where this quality factor was established, then we have no problem. The problem we face is we often will use the chamber for a different beam. And that I will leave it for next time, inshallah, where we are going to talk about the MDW calibration coefficients further, inshallah. So this is my last slide for today. Are there any questions?
Thank you, Doctor. It was a great topic to cover. Yes, I do have one.
Okay.
So, can we use NDW calculate dozen medium for heavy ions? Because I don't think we're gonna have the same NW heavy ion. Because you treat the gas in heavy ion, we treated the N gas as a changeable infinity. You know, the